So, last time we had left off, we were talking about Faraday's law, we were talking about magnetic circuits, and we hadn't gotten to the point of doing an example yet. I want to see how much more do we have. Okay, so we'll move on to chapter 9 today, into synchronous machines, and I think that that'll be good to get out of the. We spent a long time in this chapter, but it's a pretty packed full chapter, so I don't feel too bad about that. And at the end of class today, I'm going to assign the homework from the book, which will be due next Thursday, right before spring break. So don't let me end class without assigning that homework, because I want to make sure that's out there today. So for the structure of figure 2.26, which I'm assuming is the one from the previous, it's this picture here. Okay. We have the following attributes. The flux linkage is going to be represented as a oscillating function with a amplitude of phi max and sine of omega t. The number of turns is 300. The frequency 60 hertz. And the cross-sectional area is 10 centimeters squared. And the peak flux density is equal to 1.5 Teslas. Okay. So it asks us to calculate what is, again going back to this picture, what is the electromotive force, right, that would cause that magnetic field to be generated. Okay, so this is not a very difficult problem, but I think it's a good example to go through. This is going to be the other variety of problem that you can see on your midterm exam, right? There's going to be a lot of systems problems, three-phase, AC, like all the stuff we've been going through, obviously power factor correction, and then there's the magnetic stuff, which we're going to be applying today when we get into chapter 9 and start talking more about synchronous machines, okay, which is the basis for generators, and some types of loads are also classified as synchronous machines. So the first thing that we're going to do is calculate the frequency in radians per second. It's a no-brainer. Okay. $377 is the value, which is a number you'll become very familiar with in this class. Is 377 over and over again. Second thing that we need to do is we need to calculate our flux density. or relate our peak flux density to our peak flux. Okay, because we do not know what this value is here, but we do know what this value is right here. And so there's a relationship between those two, which we know. We know, so calculate peak flux from peak flux density. Okay, so we know equation 259 tells us that phi is equal to B times A. Right, area and the density. And so we plug in these values. We have 1.5 Tesla times 10 centimeters squared. If we want to make that a little bit easier on ourselves, 10 to the negative 2 squared. And so, well, let me do it the way I did it in the original notes, because I think it's important to show that. One thing that you have to be very good with in this class is taking care of units. And so just getting used to doing things in this way. So we want to convert to meters from centimeters. So we know the conversion factor, right, is that there's 1 meter for every 100 centimeters. If we want to cancel out our centimeters, we need for this to be squared, right? And so when we incorporate that conversion factor, we end up with a value of 1.5 milliwebers. And that is the peak flux, maximum flux. Next, we'll define what our oscillating flux looks like. And so that's going to be 1.5 milliwebers times sine of 377t. Again, right where that is our mega value, and this is our peak flux. And then now we're going to use Faraday's law to calculate what the electromotive force is. And so this is equation 265 from the text. And it tells us that E of t is equal to n, number of turns, the derivative with respect to time of our flux. And so now we can plug in essentially everything we know. We know the number of turns is 300. We could take the derivative of our value here. So I can go ahead, I'm going to go ahead and pull out the 1.5 milliweber and take the derivative of the time varying component, which is the sine of 377t. So the derivative of that, right, is going to give us 377 times cosine of 377t. Okay, and so let's put everything together. And I'm going to try to be very careful with the values here, because this, I mean with the units. Okay, so this is 300 turns, right? This is 377 radians per second times cosine of 377t. And the unit for that is included right here, right? That's the milliwebers. Okay, so what we need to do is to make sure that all of these work out together. So when we multiply all the numerical values together, we end up with 169.65. Cosine of 377t. And then the units we have are webers. We have radians per second. And then we have the turns. And I just scratched them both out. Hold on one second. Sorry, I did something and I'm not sure why I did it. I want to check. I'm going to come back to these notes, and I did something in my previous notes which is not right in terms of taking care of these units. I know why turns goes away, because turns is actually unitless, but I think that, because what we should end up with is webers per second, which is volts, but that, the way I have it set up is not correct. So as opposed to trying to figure that out right here, which is going to take a little bit of me looking at some of my other previous notes, I'm going to leave a little bit of ambiguity with the units. I will clear it up before I post it, so just make sure, and I'll write a pretty detailed note as to what happened. So just make sure when you're reviewing, go back and take special note of this part. And I'll put a big question mark so I remember to fix it. But anyway, the main takeaway there is, right, how we can use Faraday's law to calculate what the EMF was. Okay, so next. We're almost done with Chapter 2, and I'll leave myself some room to fix the units. So I'll go down here. I think this is the last section. So section 2.8.8, which is leakage and magnetizing inductances. All right, we've talked about this a little bit. If you remember when we were first discussing the basics of magnetic fields, we were talking about how, right, we have flux lines that connect two different sets of coils, okay? And so the effect of one on the other, that could be a magnetizing inductance, right? If you have a current flowing through a coil on one, that would generate a flux, which if it connects with another set of coils would magnetize that other coil, okay? So that's a magnetizing flux. That's like the flux that makes it through to the other side. And then we have the leakage flux, which corresponds to leakage inductance, and that would be that which doesn't connect with the other side, right? It escapes into the air, or either takes some sort of a path through the ferromagnetic material that doesn't connect with the other set of coils. Okay, so the first thing here is that we know magnetic cores guide flux cannot write today. Just like inductors, conductors, not inductors. Conductors guide current. Right? From a pure physics perspective, current could take any path, right? Flow through the air, arcing, all that type of stuff. But we know, right, that's going to take the path of least resistance. That's the reason why all the electricity flows through this wire as opposed to just going all over the place. Same thing with the magnetic core, right? The magnetic core is going to be the path of least reluctance. And so the flux will naturally flow through that core. And so there's two values that we have to be familiar with. Let me write these down and then I'll talk about what they mean. No, this is a, I can never remember. It's a sigma, right? Sigma. So what are we showing here? That the conductivity of copper is significantly higher than that of air, right? Which is why we normally don't worry about arcing. And there's just, the copper conductor would have to be so completely saturated in order to raise the effective value of that to a point where whatever electrons are left over would say it's the easier path is to flow through the air. Okay? But you'll see that our mu value, and what do we call? Mu is our relative so if you go back here, you'll see mu represents, well, it's our permittivity value, with mu m being the permittivity of the core in the linear region. Okay, so mu core, I can also, I'll write this, and we also say mu m. So what you see is that the permittivity of the core is not as high relatively when compared to air, to free space. So this is the reason why leakage inductance is much more of a concern than leakage current, right? Any current that would be flowing through the air. For electric circuits, it's not even a consideration unless you're doing some really high voltage, sort of very specific calculation. You would not consider that at all. But for magnetic circuits, because the difference is not as stark, we do have to consider it. All right. So we have figure 2.28 from the text, which essentially shows a magnetic core.
So do a lot of our technology depend on that difference between the, right?
I mean, yeah, if
Motors wouldn't work, right? If those.
well, no, I mean leakage inductance is not no, not necessarily a good thing. Motors would still work because the leakage inductance is just talking about the magnetic flux that doesn't flow through the intended path, right? Even if you don't have a magnetic core, you can still have leakage inductance. It would just be whatever lines don't, like let's say you have two sets of coils that are just, there's no magnetic core in between them, they're just connected, I mean they're just sitting next to each other. You would still have magnetizing inductance, which would be flowing through the air, through the separate coils, and then you would have a leakage inductance. The difference there is it would be, the way you calculate the leakage inductance would be different because the permittivity of the path is the same for both. You're still going to have a leakage inductance. So the leakage inductance is not, in any case that I know of, is never the one doing the work for you, right? So even for the motor, it's the magnetizing inductance that's conducting the the energy from the rotor to the stator or vice versa. Okay, so let's take a look at this example here. So this is a magnetic core, which I don't know if I've done too good of a job of explaining what that is, but for something like a transformer, it's not, the two coils are not just sitting next to each other floating in air. They're both wrapped around a common piece of really big piece of iron. And this iron, right, provides the optimal path for our flux to flow. Okay, so we have here, as usual, our wrapped coil. Okay, we have our EMF, which is exciting this. We have the direction of our current flow, which looks like this. Then we have our fluxes, okay? And so our magnetizing flux is taking the full trip here, right? If there were two sets of coils that would be lined up next to one another, and they would be connecting the two. But in this case, this is a self-magnetizing flux. The leakage right? Looks like that. And right, again, I'll just write it. So magnetizing flux and this is the basic design you'll see for a transformer when we get to transformers. For a transformer, you just push this one coil up a little bit and you have a second set of coils that are right below it. So they're not connected electrically. The power is not flowing from the primary to the secondary set of coils electrically, but flowing magnetically as this flux conducting through the magnetic core. Now normally, quick note here, what the heck is going on? So we don't consider the individual components of the leakage flux. We just say there's leakage flux that will encompass all the red lines, and then we have magnetizing flux, which is the gray line, which actually has lots of little gray lines inside of it. Yes?
Is the left side of the leakage running counterclockwise?
Yes, it should. Right, because they both have to follow the right-hand rule in terms of, they have to both, if the current's flowing this way, they both have to be flowing upward. Okay, so now some notes here. So leakage inductance, or leakage flux, however you want to say, flux or inductance. That's supposed to be a slash. Makes magnetic circuits more difficult to analyze. especially as compared to electric circuits. And so you'll see use of methods like the finite element method. Has anyone ever heard of that finite element method? You know, can you give me a little mini explanation, or?
You sort of take little sections and analyze them and then sort of add them all up.
Yeah.
Like calculus.
It's sort of like a weird, almost like linearization on like a 2D or a 3D scale, where you break the object into small, tiny pieces, and then you analyze each piece, the interaction of the pieces on one another individually. And right, the smaller you make the pieces, the more difficult the analysis becomes, but the better answer that you get. Now the good thing is, we can make this easier if we apply some assumptions. So that's what we're going to do. We will not be using the finite element method. We'll be applying some assumptions that will help us analyze. First, we're going to assume that the magnetizing and the leakage inductance link all the coils, because one thing which I didn't draw here is, right, you can have little mini leakage loops which don't necessarily, here we have 4 turns, that don't necessarily connect all 4 of the coils with one another, right? There will be a leakage inductance component that's just corresponds to each one. So again, going back to the idea of aggregating these, now we're going to say there's just one leakage flux, and it's going to be this outermost loop here, the one that connects all of the coils together. And so this assumption allows us to break the flux and inductance into 2 different discrete terms, so we've already I started off explaining it using the assumption, and now I'm just sort of reinforcing that. So this assumption allows us to define 2 discrete values. Right, we have our, when in reality there should be lots of phi L's, right? There should be lots of different paths that we encounter. And so equation 267 from the book says, right, the total flux is equal to the magnetizing flux plus the leakage flux. And now we can take that equation and we can relate, so we can relate 267 from flux to flux linkage, and then you'll see that's going to lead us down the path to be able to work backwards to Faraday's law. So we know that flux linkage this should be peak field intensity, not peak flux density. I gotta fix that. So flux linkage, right, is equal to N times phi. And so we can break that up into N times phi m plus phi l. Again, the reason why we can do that is because the number of turns is assumed to be constant for the leakage, right? If we were considering all those mini loops, the n wouldn't be the same for each one. There would be different n values. And so, well, I don't need to write this. It's what I already said. Okay. And now we know that relationship exists. So what we can say is that, this is equation 270 from the book, we can say that our L self-inductance, which again, we're just talking about self-inductance because there's no second coil here, right? This is all self-magnetizing and then leakage related to it itself, right? We're not discussing the case yet where there's a second set of coils. Did you have a question?
Was that, you wrote can't there, that was correct?
Where does it say it?
The last line you made, or last line.
Yeah. That would be an awkward statement to write. I'm telling you all the things you can't do. I'm just going to list them out one by one. All 700 things you cannot do. All right, so we can convert magnetizing inductance plus the leakage inductance, which we're going to switch over to using a cursive L. And so this is our leakage flux divided by our current. And this is our magnetizing flux linkage divided by our current. That just relates all the different values together. You can see the different permutations of them. All right. So now you can see we're getting to the point where we can start drawing this as a circuit. Okay, like a circuit, the kind you're more used to seeing from like ENG212 from electronics. And that's essentially the point that we're trying to get to, right? If you remember electronics, right, in chapter 3, we had all that physics stuff to do with valence electrons. We wanted to get it represented as a V and I relationship. Same thing here. We most, for 99% of cases, don't want to be dealing with flux leakage, magnetic field density or intensity. We want to be dealing with V and I. And so the inductance is the way that that we can do that. So figure 229, sorry. Presents the magnetic circuit as an inductance-based electrical circuit. So this guy here, right? Now we can represent that as an electrical circuit. And this is not a trivial thing. I know we spent a lot of time on this chapter, but this is not trivial because when we try to represent synchronous machines, when we try to represent transformers, doing all this up front means we can skip straight to representing things as electrical circuits, which makes it easier for solving problems. If you want to stick a synchronous machine or a transformer into your circuit, the second representation, which we're about to present, is going to be a lot easier to use. Okay, so we have same values. We have our EMF, which we have seen. Okay. We have our and I'll label these in 1 second. So we have our magnetizing inductance, and we have our leakage inductance. And our current is the same current. And that's pretty much it. We have a value over here, which we're going to call E sub m, which is the component of the EMF, which is contributing to self-magnetizing. And then we have the other component, which will be that which is contributes to the leakage.
Professor?
Yeah?
They're not physically at right angles to each other, are they?
No, this is just a circuit. You know, anything when it's drawn like this, and if it's not a schematic, right? The orientation of everything is completely, you know, there's no connection there. So, and this voltage here, because we know right, we could give it a name. We could call it the leakage EMF, but we'll just simply define it by the relationship between current and voltage for an inductor. And so another way of so we can draw a little bit more of a practical version of the circuit below, where we're going to incorporate just a few more things. So we'll have our terminal voltage. The terminal voltage so we will have a resistance which will represent the resistance of the coil. We will have a leakage inductance still. And so now our E of T will fall here. And we still have our, and the one way I drew it, which I'd like to do it the same way. Remember that this is not part of the circuit diagram, but it's just a nice way to show what's going on. Right, you can imagine the inductor looking like that, where it's generating this magnetizing flux. And so this, just like in the picture again, is still the magnetizing flux, and this is still going to be our component of the EMF that contributes to the magnetizing. So what are the differences here? So this voltage is the induced voltage. And then we have our terminal voltage. And the main difference there is just we're taking into account the internal resistance of the coil itself. So the circuit above and the circuit below are just very, very slight variations on one another. But you will hear, in the textbook, they'll talk about the terminal voltage versus the induced voltage, et cetera, et cetera. And so right, we can induce this using our good old KVL. We know that the terminal voltage will be equal to the resistance times the series current plus the leakage inductance derivative of T or of I with respect to T plus and yes, you can combine the two elements, the two inductive elements together. And this would be the actual terminal voltage that you see when you're hooking up your equipment to this thing, or when you're using a scope to take a look at what's going on. All right. So we're going to start on Chapter 9. I'd like to take a 2-minute break because it's been using the assumptions for complex analyses almost gives you the same result as if you didn't use those assumptions. So I guess what I'm saying is I'm trying to hit on the parts which I think are the most interesting to power engineers that are actually working in the field. Okay, so Chapter 9. So the synchronous machine is essentially the generator, okay? There can also be loads that are synchronous machines, very large industrial loads, although not all motors are synchronous machines. There's lots of different types, but for smaller loads, a lot of them will be induction motors. And we'll talk a little bit about the difference between a synchronous motor and an induction motor later on in this chapter, but it has to do essentially the synchronous machine is locked into being synchronous with the waveforms, the electric waveforms. whereas an induction motor is not locked in that way. There's an element called slip. So the motor can drag behind the rotation. There can be it can fall behind the actual waveforms themselves. Okay, so a couple points here. Not going to write all of them down. Right, we know that, so synchronous machines, they allow us to take mechanical power and convert it to electrical. And this is the way that most power is generated. So most power is generated this way. The really big exception would be solar, right? Solar generates DC, and so doesn't use a synchronous machine, but wind does, right? Because we still have rotational energy. Hydro does, because we still have rotational energy. And then obviously anything that's fossil fuel based would also use a synchronous machine, because you're using that to generate heat, generate steam, goes through a turbine, and then rotational energy again.
So it's called synchronous because the generation is in sync with
You can directly relate the angle of the rotor to the angle of or the phase of the waveform that's either coming into it if you're considering it to be a motor, or leaving it if you're considering it to be a generator. Yeah, those are locked in step. And we'll see why that is when we look at the internal mechanics of the way the thing works. So they use what's called voltage excitation systems to regulate the voltage magnitude, as well as, we'll see later on, it can also be used to control the reactive power output. So we'll see another way to perform power factor correction, although that's not really the term that we would use in this instance. But to control reactive power is we can manipulate the excitation of the field windings of the generator. And so the real power output is going to be proportional to the mechanical power in. Pretty straightforward relationship. If you want to get more power out of the generator, you turn up the heat, you start letting more steam into the turbine, and the mechanical torque that's applied to the rotor gets higher. The reactive power, which I said a second ago, is going to be related to a value which is IF, and this is the current along the field windings. And that's the same thing as saying we control the excitation of the rotor. And so a lot of this stuff, I mean, some of these terms don't really mean anything at the moment. It's a little bit of an intro, and as we get into the chapter, a lot of these terms, especially voltage excitation, will start making more sense.
Sorry, what's I sub F?
I sub F is something we haven't introduced yet. That's the reason why I was looking at this and kind of deciding what I wanted to say. If you divide, so you have the stator of the generator, you have the rotor of the generator, the part that turns, and the wire inside of the rotor is called the field winding. So to control excitation, you essentially control the amount of current flowing on that field winding.
And that's divided by or slash?
That's just slash, meaning the field winding is synonymous with excitation. All right, and so we can divide the generators up into two categories. One category we'll call the fast reacting, the other category we'll call the slow reacting. And so fast reacting generators are let me write everything and then I'll talk. So really what we're going to do is split it up into big and small, fast and slow. Smaller means faster. And I'm a little bit hesitant to use the term hydro for the slow one because there could be some other types of potentially really, really large. I guess coal wouldn't really operate that slowly, but I guess there could be some non-hydro implementations which would be representations of the slow. But anyway, that's the way we're splitting it up. Fast versus slow, big versus small. And we're going to be focusing more on the first instance of them. And so we can also give these some other attributes. So this will operate at 1800 RPMs approximately for 60 hertz generation. And it will have 2 poles, meaning that the rotor will only have 1 north pole, 1 south pole, okay? As opposed to, you can have implementations where there's multiple poles that kind of go around like that. And that's used for the slow moving generators for when the actual rotation is much slower than the 60 hertz, right? When you rotate at the 1800 RPM with the 2-pole machine, you generate 60 hertz. So for the slow moving, we have less than 1800 RPM. And we will have I'll put that little line through hydro because that's sort of like hydro or anything that moves slowly. Wind is okay. So wind is a little bit. So yes, but they also wind uses gears. Normally, there's a gearbox in order to bring the frequency up. So it falls in the first category, but again, you would in order to have a full understanding, you would have to also include the gearbox. Whereas for a hydro, they don't use a gearbox. They don't use any mechanical method in order to increase the rotational frequency. And that has to do with the fact that, at least for the hydro, it's a controllable constant slow frequency, whereas for the wind, it's a variable low frequency. really, to make a long story short, we're going to be dealing with like the classic medium-sized coal or gas or natural gas powered generator, which essentially anything that has two poles and operates at 1800 RPM, as opposed to other variations of that. And honestly, the basics are not going to be that much different. We'll touch upon how you can apply these same basics to slower moving generating stations. It's just that we're not going to go into all the details of it.
Just out of curiosity, where is nuclear? How fast those turbines?
Nuclear would, I believe most nuclear stations run with as fast because really most times when you have steam or heat, you can generate very fast rotation. So, I mean, I guess for the second one, it really would only be hydro. I'd have to think about that a little bit more. But hydro is the main example of one where they don't run it at the higher rotational speed. And there's also shades of gray in between. One second, because hydro might have 8 poles, 10 poles, where it's running much, much slower. And then there might be a steam-powered station which runs at 900 RPM and just has 4 poles, right? And there's a big difference in how far we can go with that train of thought.
Is there a significance to the RPM being 1800 as like set standard for dispatch generators?
Well, we'll see in a second. That translates if you take into account RPM and the number of poles, and then the rotational rate, that'll give you essentially 60 hertz. That's the value that lines up with 60 hertz.
So ever try to go over 1800?
Well, so the thing is that you can use multiple sets of poles to take a slow mechanical frequency and make it a faster electrical frequency. You don't really ever want to generate more than 60 hertz unless you're talking about some very special system which runs on high frequency AC, and I don't really know of anything that does that. It's possible. I just don't think there's a real application for it. Okay, so this picture I'll include in the notes, but I'm not going to redraw it. So this is the basic pieces and elements of our synchronous machine. So we have the rotor, which is in the middle. We have the stator, which is on the outside. We have stator windings, which you have one set here, here, and here. I think we looked at a diagram that was similar to this in that first lecture, the PowerPoint lecture that we did. And then we have the field winding, which usually there's only one set of field windings. And this is where the number of poles comes into play. If you only have 2 poles or one set of poles, you only have one field winding. If you have multiple sets of poles, you would need multiple field windings. And so, we know from what we learned in the magnetic, in the end of chapter 2, where we talked about magnetics. So our current flowing along the field winding, which again looks like this. The hole is where it comes out and the X is where it goes in. So you can imagine it sort of like projects out of the screen. So if you look at that going the right hand rule, okay, so this is my thumb. The wire would be here, which would generate an electric magnetic field flowing in that direction, okay, which is shown by the big red arrows. So that's the excited magnetic field. Now, that is going to cause a current to flow on the stator windings. The way we can examine the direction of that and relate the two of them together is we can think of it using like every action has an opposite and equal reaction. So the excited magnetic field will be zeroed out by the induced magnetic field. Okay? So when you think about the current flowing on the stator windings, the direction of that is such that the induced magnetic field and the excited magnetic field net out. It's sort of like when you push against the desk pushes against you with that same amount of force. So when you excite this magnetic field using the field winding, the current flowing through the stator winding creates a magnetic field that opposes it. Okay? But it's really the power flowing in one direction, right? Current turns to magnetic field excites current on the stator winding. Does that make sense? I see some confused faces. The terminology of excited magnetic field and induced magnetic field can be a little bit confusing. But again, it's just, I think what I was really trying to show with this picture is how you can see the relationship between the directions of the currents and the directions of the magnetic fields. Again, being opposite to one another. And so, right, two things. The induced stator current, well, a couple of things. The induced stator current, this is the current that's going to be flowing out of the machine, okay, and going to wherever the electricity is needed. Number two is that the strength of that current is not dependent solely on the field winding current, but also the rotation, right? Because no current is generated unless the magnetic field is experiencing a change, right? It's d phi dt, not just phi, okay? And so it's the rotation that actually provides the change in the magnetic field. Because when they're lined up like this, the flux linkage between the field winding and phase A is maximum. But what happens when you take it and you rotate it 90 degrees, you see that there's no flux linkage or very minimal flux linkage between the field winding and phase A, right? It's like when the two coils are like this, they share a lot of the flux lines. When they're like this, right, they don't share any of the flux lines. And so this represents the rotor at 0 degrees, which is field winding lined up with phase A. This is a picture from a textbook that we used to use, but it's a really good picture. And so it shows it with a little bit of a different, well, it's a little bit more complete. It shows all three of the phase windings, of the stator windings, A, B, and C. Shows our field winding, as well as our field current. Again, we have the rotor, which is the part that turns. We have the stator. And then we have the MMF of the DC winding, right, which is the magnetomotive force. We have the D axis and the Q axis. This is one of the things that we'll be using in this chapter. The D axis, you can see, lines up with the direction of the magnetic field. The Q axis is orthogonal to that and lags the D axis by 90 degrees. Because you can see the direction of rotation is like this. This is an example of a multi-pole machine. Okay, so this is a 4-pole machine. It has 2 sets of field windings, and it has, instead of ABC, it has ABC, ABC, right? So for every rotation of this machine, instead of getting 1 period of A, 1 period of B, 1 period of C, you'll get 2 of A, 2 of B, 2 of C. Meaning that you can rotate this rotor at a slower frequency and still get out your 60 hertz. So essentially you could rotate this at 900 RPM and still get out your 60 hertz. This is also a example of what's called a salient pole machine. So there's round rotor and salient pole rotors. So the round looks like this. It's just round, okay? And then the salient pole, what they do is they take the rotor and they sort of like dig out certain pieces to make this almost a hammer shape. And then they wrap the field windings around that part of it, which what it does is it creates a more directed magnetic field because you're taking away some of the additional high permeability core on either side. We're not going to go too much into the differences between round rotors and salient pole rotors just because we don't have the time in this class. Okay, I know we're getting close to the end. I just want to finish these pictures. Okay, well, that's it. So we'll stop there.